You know that feeling, like when you're cramming for a massive high-stakes exam?
Oh, yeah. Freaking out at the last minute.
Exactly. You sit down at a desk at like 2 in the morning, totally surrounded by textbooks, and you just try to ingest an entire semester's worth of dense information all at once before the sun comes up.
Right, which is exhausting, just forcing it into your working memory.
It requires a ridiculous amount of brain power to hold it all in. And, well, the worst part is, once the exam is actually over, your knowledge base is essentially locked in.
Yeah, the test is done.
Right. If a groundbreaking new piece of research drops the very next day, your exam score doesn't reflect it. You've already taken the test, so your model of the world is basically frozen.
Which is exactly the limitation traditional machine learning architectures face.
Yeah.
I mean, the moment the engineers finish running the training data and, put their pencils down, that model is effectively static.
Welcome to the deep dive. We have a seriously fascinating piece of source material on the table today. We're exploring a comprehensive Wikipedia article on online machine learning.
It's a huge topic.
It really is. And, if you are listening to this on your commute right now, or maybe you're working out, our mission today is to cut through all the dense algorithmic jargon and show you how machines are actually learning to adapt in real time, like side by side with you.
Because the real world doesn't work like that late night cram session.
Exactly. The real world never stops generating data. Okay, let's unpack this.
Well, what's fascinating here is that the transition to online machine learning allows algorithms to dynamically adapt to sequential data, basically processing it one piece at a time.
Right.
And this isn't just some theoretical computer science concept waiting in a lab somewhere. If your map app just rerouted you around a sudden traffic jam that didn't exist 5 minutes ago, that is online learning.
Oh, wow. So it's everywhere.
Completely. It's the architecture updating automated stock portfolios as the financial markets fluctuate second by second. It's spotting anomalous credit card transactions in milliseconds. We're even seeing a massive push to apply these paradigms to large language models.
Right, so they can continuously adapt and update their factual baselines after their initial training runs, which, are incredibly expensive.
Exactly.
So to really appreciate how much of a paradigm shift that is, I think we need to look at the baseline standard the industry uses, which is called batch learning, and why it's currently hitting a massive brick wall.
Yeah, batch learning is struggling. In a batch environment, you generate your best possible predictor by feeding the entire historical data set into the machine simultaneously.
All at once.
All at once. The algorithm churns through the entirety of the data, finds the patterns, and just spits out a finalized model.
Yeah.
And for a long time, when data sets were relatively small, that worked brilliantly.
But not anymore.
No, we have scaled way past the point where that is physically viable for a lot of applications. When you're dealing with modern web-scale data sets, batch learning becomes computationally impossible.
Because it's just too much data, right?
Right. The volume of data literally cannot fit into the computer's main memory, or RAM, all at once.
Yeah.
When a system tries to load more data than the RAM can hold, it starts paging or swapping data to the hard drive.
Which is agonizingly slow.
It is. It effectively chokes the system. This forces engineers to use what are called out-of-core algorithms, where the system has to process data from the storage drive in chunks.
Yikes. And beyond the hardware limitations, the other major failure point for batch learning is dealing with time series data.
Oh, absolutely.
Like if you're building a predictive model for international financial market prices, you can't train your model on all the data because, well, tomorrow's data hasn't happened yet.
Right. The underlying environment is constantly shifting. Economic policies, consumer sentiment.
It never stops.
In statistical terms, the underlying distribution of the data is non-stationary. The rules of the game are changing while you are actively playing it.
I look at it this way. Batch learning is like trying to memorize an entire public library. The moment the librarian adds a single new book to the shelf, your knowledge is technically incomplete.
Yeah, out of date immediately.
Exactly. And to update it, you have to read the entire library from start to finish all over again just to integrate that one new plot line. Whereas online learning is like reading a single page, updating your worldview based on the new information on that specific page, and moving on to the next.
That's a perfect way to picture it.
Imagine your email spam filter waiting until the end of the year to run a massive batch learning session just to learn what a newly invented phishing scam looks like.
Your inbox would be completely compromised for 12 months. You'd be ruined.
Seriously. So to understand how we engineer a system to learn page by page, the source outlines the statistical view of the problem.
Yeah, so a machine learning model never actually knows the true distribution of data. It doesn't possess, like, a God's eye view of all possible spam emails or financial shifts that will ever exist.
It's basically flying blind to the big picture.
Right. It only has access to a finite training set of examples and, crucially, a loss function.
Ah, the loss function. This is our North Star here. For you listening, it's the mathematical delta between our prediction and reality. It basically measures the penalty for a bad prediction.
Exactly. If the model guesses a stock will go up by 2% and it actually drops by 5%, the loss function quantifies exactly how wrong that guess was.
And minimizing that total loss over time is the sole objective of the system. In a pure online model, the algorithm looks at the brand new input, checks its current internal weights to make a prediction, looks at the true outcome, calculates the loss function, and makes a tiny mathematical adjustment to its weights.
But the mechanical question is how the system actually executes that math without starting over.
Right, because if we absolutely must update sequentially to avoid the memory limits of batch learning, how does the machine recalculate its trajectory every single time a new data point arrives?
Well, the text walks us through the fundamental example of linear least squares. It's a classic method for drawing a line of best fit through scattered data.
Like the scatter plots you'd see in high school math.
Exactly. Now, if you attempt this using a brute force batch approach, every time a new data point arrives, you have to recalculate everything to find the new perfect line. Mathematically, this involves inverting a covariance matrix.
And when you look at the covariance matrix, for anyone dealing with high-dimensional data, you know that tracking how every single variable relates to every other variable becomes a massive, computationally heavy grid.
Oh, yeah. As your features grow, that matrix becomes unwieldy. The computational cost is immense.
How bad does it get?
Well, the text notes that performing this naive recalculation for every new data point results in a time complexity of big O, of n times d cubed.
Okay, d cubed.
Right, where n is the number of data points, and n represents the dimensions, or the number of features in your data. Because the dimensions are cubed, if you increase your features from 10 to just 100, the time it takes to compute that matrix inversion skyrockets from 1,000 operations to 1 million.
Wow. It scales terribly.
It scales incredibly poorly.
That's an absolute death sentence for complex modern data sets. So the first solution the source offers to mitigate this is recursive least squares, or RLS.
Right, RLS.
Instead of recalculating the entire covariance matrix from scratch, RLS stores a single summary matrix, like a condensed representation of everything it's learned so far. When a new data point arrives, the algorithm performs a much simpler update to just that summary matrix.
It's a really elegant trick. It drops the time complexity from d cubed down to big O of n times d squared.
Which is huge. You shave off an entire order of magnitude in processing time.
It makes the math significantly faster, allowing the system to keep up with faster data streams.
Okay, sure, RLS drops the compute time, but I'm looking at the memory requirements. If we are tracking an infinite stream of data in a production environment, that summary matrix is still going to grow and become a bottleneck, right?
Yes, absolutely.
We haven't entirely solved the resource issue, we've just shifted the burden. As the data flows in continuously, wouldn't storing and updating that dense matrix eventually hit a wall anyway?
That is the pivotal bottleneck. And it's exactly why the field had to develop a fundamentally different approach. That brings us to stochastic gradient descent, or SGD, which just abandons complex matrix inversions entirely.
SGD is essentially the underlying engine powering the vast majority of modern artificial intelligence.
It really is the workhorse of the industry. Rather than trying to find the perfect, exact mathematical line of best fit by looking at a massive matrix of past data, SGD updates the predictor by taking a small, populated step based solely on the gradient of the loss function for the current data point.
I love visualizing this. If we visualize the loss function as a physical landscape, the gradient is the slope of the ground beneath your feet.
Yes.
The algorithm is essentially standing on a mountain blindfolded. It can't see the entire landscape like it would in batch data, so it just feels around with its foot to find the steepest downward slope, taking one step at a time toward the valley floor, which represents the lowest possible error.
That's a great analogy. And because it only takes that one step based on the slope of the immediate data point, the time complexity drops again, down to big O of n times d.
Not squared, not cubed, just d.
Just d. But more importantly, this addresses your exact concern regarding memory. The storage requirements become strictly constant.
Wait, really? Constant memory?
Yes. You do not need to store a growing matrix of past data.
Hmm.
Whether the system processes 10 data points or 10 billion, the amount of RAM required to hold the model parameters stays exactly the same.
Okay, here's where it gets really interesting, though. There is a specific mechanic the text highlights regarding how the algorithm takes those steps. It's known as the decaying step size, or the learning rate schedule.
Yes. Crucial detail.
If the algorithm reacts too aggressively to every single new piece of data, like taking massive leaps down that mountain, it will constantly overshoot the lowest point of the valley.
Right, it'll just bounce back and forth up the opposite walls of the canyon forever.
Exactly. So by actively decaying the step size, meaning the algorithm takes smaller and smaller steps as time goes on and it gets closer to the minimum, it stabilizes and smoothly converges on the optimal mathematical truth.
It's a brilliant stabilization mechanism. However, and this is a big, however, gradient descent in this pure form, works remarkably well for relatively simple linear problems.
Yeah.
But complex real-world data is rarely linear.
Yeah, you cannot just draw a straight line to separate user behavior patterns or financial anomalies. The data points are tangled up in incredibly messy, nonlinear ways.
So to handle nonlinear decision-making on the fly, the text introduces kernel methods.
Okay, kernels, how do those work?
Well, when you have a data set that cannot be separated by a straight plane in its current dimensions, kernel methods use a mathematical function to project that data into a much higher, sometimes infinite dimensional space.
Infinite dimensions, wow.
Yeah. By adding these dimensions, the data stretches out, and suddenly, a straight line actually can cleanly separate the categories.
Projecting data into infinite dimensions mathematically solves the nonlinearity problem. But kernel methods create a totally new architectural problem for an online system. The text points to the representer theorem.
Right. This representer theorem basically states that to evaluate this infinite dimensional kernel space for a brand new piece of data, the algorithm actually has to reference the past data points.
Which completely breaks the pure online learning paradigm we just talked about.
It does. The algorithm can no longer just take a step and forget the data like it does in pure stochastic gradient descent. It must store a subset of previous examples, often called support vectors, to define that complex boundary.
So it becomes a hybrid approach.
Exactly. You gain the ability to model highly complex, nonlinear realities, but you lose that beautiful constant memory guarantee. You're forced back into a trade-off between accuracy and memory limits.
And because we're no longer just cleanly calculating a straight line, but rather projecting data and placing bets in a highly uncertain, shifting environment, mathematicians had to reframe the entire problem.
It did.
The source introduces a broader theoretical framework called online convex optimization, or OCO. OCO abstracts this entire process into a repeated strategic game played against nature.
Yeah, in this framework, you, acting as the machine learning algorithm, must make a prediction for the current round. Then, nature, the real world, reveals the true answer, which is your loss function.
Right.
You suffer a quantifiable loss based on the inaccuracy of your prediction, you update your internal parameters, and the next round begins. The ultimate mathematical objective of this game is not to be perfect every time, but to minimize regret.
The game of regret. I love how that's phrased. To put this into a real-world perspective for you listening, think about mathematical regret like reviewing your personal investment portfolio at the end of the fiscal year.
No, that's a painful thought.
Right. You look at the cumulative returns you actually achieved by making daily guesses and trading actively. Then you compare that exact return against the single perfect stock you could have picked on day one and just held all year if you had a crystal ball.
And the difference between your active sequential guesses and the best possible fixed hindsight choice, that delta is your mathematical regret.
So how do you win this game?
Winning requires specific algorithmic strategies. The text outlines a baseline approach called follow the leader, or FTL. It's a purely greedy algorithm. At every single step, it looks back at all the past rounds and simply selects the hypothesis or weight distribution that would have resulted in the least amount of loss up to that point.
It basically just jumps on whatever mathematical bandwagon is currently winning the game.
Exactly.
Which introduces severe volatility. If the data environment is highly dynamic, follow the leader will violently swing its predictions back and forth, overreacting to whatever just happened in the previous few rounds.
So it's too reactive.
Way too reactive. To counter this, the field utilizes follow the regularized leader, or FTRL. This algorithm introduces a mathematical stabilization penalty, a regularization term.
So it fundamentally changes the incentive structure. Instead of just chasing the lowest loss, FTRL punishes the model's internal weights if they grow too large or change too rapidly.
Right.
It effectively tells the algorithm, find the lowest error, but you are penalized for drastically overhauling your worldview based on short-term noise. It smooths out the learning curve by demanding consistency alongside accuracy.
Yes, consistency is key. So what does this all mean when we zoom out? We have algorithms making dynamic predictions, constantly updating their internal weights to minimize regret, and stepping down gradient slopes. But if a neural network is continuously updating and physically overwriting its internal parameters with brand new information, what happens to the knowledge it already acquired?
Oh. You are pointing to one of the most critical vulnerabilities in the entire architecture of continuous learning. The source literature formally refers to it as catastrophic interference, but it's commonly known as catastrophic forgetting.
When you look at the architecture of a neural network, the knowledge isn't stored in neat little databases, right? It's distributed across the weight connections between artificial neurons.
Right, it's the web.
When the model processes incrementally available information from non-stationary data, meaning the fundamental rules of the incoming data have shifted, it has to adjust those weights to accommodate the new reality. And by doing so, it can completely overwrite and destroy the delicate web of pathways that represented previously learned patterns.
The new knowledge physically evicts the old knowledge.
Imagine you spend 5 grueling years learning to play the piano. You master the instrument. Then, you decide to take an intensive week of tennis lessons.
Okay, I see where this is going.
Because your brain, in this analogy, suffers from catastrophic forgetting, the specific neural pathways you use to swing the racket forcefully overwrite the pathways you used for finger dexterity. You walk back to a piano and have completely forgotten what a keyboard is or how it functions. The new data obliterated the foundational data.
And applying that to enterprise systems is highly problematic. If you deploy an online machine learning model to detect credit card fraud and initially train it on European transaction behaviors, it'll perform exceptionally well.
Right.
But if you then expand your business and start feeding it a continuous stream of real-time data from Asian markets, the model adjusts its weights to understand the new Asian fraud patterns. In the process, it might completely lose its ability to recognize the European fraud patterns it used to catch effortlessly. Yeah, it optimizes for the present at the total expense of the past.
It basically induces a form of algorithmic amnesia. This is exactly why the text highlights continual learning paradigms as a massive, heavily funded area of active research. Continual learning specifically attempts to solve this plasticity stability dilemma.
How do you design an architecture plastic enough to learn new things, but stable enough to protect its core foundation?
Exactly. It's absolutely essential for autonomous agents interacting in the physical world. A self-driving car cannot learn how to navigate a new type of snowy intersection and suddenly forget how to recognize a standard red light.
The same applies to large language models. If an LLM is continuously adapting its weights based on individual interactions with users to stay current with modern events, engineers must ensure it doesn't catastrophically forget the basic logical structures of language.
Or its safety guardrails, just because it ingested a million new slang terms from social media.
Right. Balancing that adaptation is an incredibly complex engineering hurdle.
So we've covered the theoretical math, the shift to sequential processing, and the danger of catastrophic forgetting. Let's look at how this is practically implemented in the development environments engineers are using today. The text highlights 2 major open-source implementations that power a lot of this infrastructure.
Yes.
First is scikit-learn, which is practically ubiquitous in data science. They provide out-of-core tools like an SGD classifier and something called mini-batch k-means.
Mini-batch represents a highly practical compromise between pure online learning and traditional batch processing. Rather than updating the internal weights after every single individual data point, which can introduce a lot of erratic noise into the gradient descent, it processes a small, manageable batch of data.
Like a few hundred examples at a time.
Yeah, say a few hundred examples. It smooths out the gradient steps while still bypassing a massive memory requirements of full batch learning.
It's a really pragmatic middle ground. But the second tool mentioned in the source is where the engineering gets remarkably creative, Val-Paul-Wabbit.
Setting aside the fantastic name.
Right. Great name. The text details a specific mechanism it utilizes called the hashing trick. In an infinite data stream, you don't just have an infinite number of rows, you often encounter an endlessly expanding number of features, like unique user IDs or novel text strings.
And tracking an ever-growing dictionary of these features will eventually exhaust your memory.
Totally. The hashing trick circumvents that entirely. Instead of maintaining a massive lookup table that assigns a unique index to every new feature it sees, Valpol-Wabbit passes the raw feature data, like a text string, through a mathematical hash function.
Right, which is brilliant.
It really is. This function takes any arbitrary piece of data and mathematically maps it to a specific integer index within a fixed size array. It essentially creates a predetermined hard-coded number of buckets.
And when a new feature arrives, the hash function instantly calculates which bucket it belongs in.
Exactly. Even if two different features occasionally hash into the exact same bucket, which is a collision, the mathematical models are robust enough to handle the noise, provided the array is large enough. It bounds the memory footprint of the feature, set entirely independently of the amount of training data flowing in.
So you can process an infinite fire hose of data with a strictly capped memory limit.
Yes.
Well, if we connect this brilliant piece of engineering to the bigger picture, the text clarifies that utilizing tools like Valpol-Wabbit or Scikit-learn's SGD hinges entirely on which of the two interpretations of online learning you are executing.
Because the objective dictates the interpretation.
Exactly. If you're dealing with a truly infinite stream of real-world data like analyzing a continuous, never-ending feed of global sensor data or social media posts, you are utilizing online learning to minimize what statisticians call the expected risk.
Your ultimate goal is to build a model that performs accurately on the true, fundamentally unknowable distribution of future unseen data.
Right, you're modeling a moving target. But the second interpretation is far more pragmatic and resource-driven. Imagine you possess a massive finite data set. It's completely static, but it's simply half a terabyte in size and physically cannot fit into your workstation's RAM.
In that scenario, you use the exact same online learning algorithms, like stochastic gradient descent, merely to loop sequentially through the static data point by point to save memory.
You're not trying to predict an unknown future environment. You are simply minimizing the empirical risk of the massive data set you already possess on your hard drive.
It's the exact same underlying mathematics applied to achieve a completely different philosophical and practical objective.
Yes, one explores the unknown continuous frontier, while the other is just an efficient mechanism for processing a warehouse of data too massive for standard hardware.
We have covered some profound architectural shifts today. We journeyed from the sheer computational limits of batch learning cram sessions, where memory swapping physically chokes the system, into the dynamic necessity of online learning. We broke down how techniques like stochastic gradient descent abandon matrix inversions to keep the mathematics incredibly fast, stepping carefully down the gradient slope while keeping memory requirements strictly flat.
And we also explore the complex trade-offs, from the infinite dimensional projections of kernel methods demanding memory back, to the very real threat of catastrophic forgetting physically overwriting a model's foundational knowledge.
And we saw how the hashing trick in tools like Valpol-Wabbit allows engineers to process infinite streams without crashing the system. Why does grasping this underlying architecture matter to you? Because we are rapidly moving away from static technology. The next time your financial app adjusts your portfolio based on a sudden market swing, or your email catches a phishing attempt that was invented 3 hours ago, you will know exactly what is happening under the hood. It's online machine learning, mathematically calculating regret, and adjusting its worldview in real time.
And this raises an important question, something for you to consider long after this deep dive ends. If the research community manages to fully solve the catastrophic forgetting problem within continual learning,
Which would be a huge deal.
massive, it introduces a profound architectural possibility. Could a single, continuously adapting machine learning model essentially lave and compound its knowledge indefinitely? A system capable of evolving its understanding alongside human history, adapting to every new paradigm and era of data a century from now, without ever requiring a system reboot or a fresh batch-learn start.
An intelligence that just continuously reads the pages of history as they are written, compounding its understanding without ever having to unlearn the past. That is a truly wild thought to leave off on. Thank you for joining us on this deep dive. We will catch you next time.